Okay, let's talk about continuous random variables. So specifically, let's say I have a random variable and its range happens to consist of one or more intervals of the real line. Okay, as an example, let's say I'm measuring a voltage and I think the voltage falls between -5 and 5 volts, and I've decided to model any possible voltage in that interval as something that I could measure, quantum mechanics aside. Okay, so we're not at that fine scale. Let's just say it can be any possible number. Okay, so the range is no longer discrete, so we can't use discrete random variables. We need a new kind of random variable to deal with this. Okay, before we kind of talk about what that's going to be, let's motivate all of the framework that we're going to see with an example. Okay, so it's going to be a simple example, and there's no need for you to be able to reconstruct all of this modeling from scratch, but it's going to help you understand why we're doing what we're about to do. Okay, so I have a wheel, let's say a wheel of fortune, and I'm going to say that it's a diameter of 1 meter, and I'm going to spin it very, very fast, okay, and let it go and then record where it stops. Okay, so here it is, it's spinning, and I record where it stops. If it's spinning very, very fast for a long time, it's reasonable to say all stopping positions are equally likely. And so overall, we have a random variable, x, that is likely to take any value on the interval 0, 1. Okay, so what is the probability that x should be equal to little x for some value in this interval? Now, intuitively, this needs to be 0. Okay, so I shouldn't be able to pick any particular value and expect to see anything other than 0 probability. And if you remember, way back in the beginning of the course, we actually had some thing to say about that when we were talking about probability axioms, but you don't need to remember that now. You just need to know that if it was positive, then I could add up the infinite positive values between 0 and 1, right? Because they're all equally likely, and I would get probability infinity for the interval, which is not okay. It needs to be 0. Well, okay, what should we do instead? So let's try to model this scenario using discrete random variables and see where we end up. Okay, so what I'm going to do here is I'm going to divide my wheel into n equal sized pieces, and I'm going to let y be the slice that we land in. Okay, so if you want to formally model this, let's say that y is equal to 1 over n times the floor of n times x. So this is the exact way in which I'm quantizing this unit interval into n pieces. And so then the range of y is going to be 0, 1 over n, 2 over n, up to n minus 1 over n. Okay, and this flooring operation tells me how I land into each of those points. Okay, that aside, so I have my wheel. It has 2 pieces in this case, or it could have 4 pieces, or maybe it has 8 pieces. I'm just drawing some examples. I'm just going to keep doing this, and eventually I'm going to take n to go to infinity, right? And then I'm going to recover my continuum on this wheel. Okay, so the first thing I want to do here is I want to draw the PMF for each of these values of n for the slice that I land in. Okay, so for this first n equals 2, I have 2 pieces and they're equally likely. So it makes sense to just say that they're going to be probability 1/2 each. Okay, so the probability of landing in the first half is half and the second half is half. So blue is half and red is half. For the next wheel, I have 4 pieces and they're equally likely, right? So it makes sense to say that they're 1/4 each. So let's say blue is a fourth, red is a fourth, yellow and green are a fourth. I have an eighth for every piece in the n equals 8 wheel, which makes sense. And if I keep going to infinity, it makes sense that I'm going to have every value going to 0. Okay, so this is another way of seeing why it kind of has to go to 0, that the probability is getting smaller and smaller as I make these little slices small. Now I'm going to just draw the CDF. We're going to see what happens with the CDFs. Okay, so remember the CDF is just the probability that y is less than or equal to y. So the first time it's going to jump up at n equals 2, it's going to happen at 0. It's going to jump up by a half. Okay, the next time it's going to jump up is going to be at the value half. And it's going to jump up by another half and go to 1 and go on forever. Okay, now the jumps are going to be smaller when I get to n equals 4, and they're going to happen more often. So I'm going to jump up by a fourth at 0, a fourth at a fourth at 2/4, and a fourth at 3/4 until I get to 1. And then I'm going to jump up by eighths when I get to the n equal eighths wheel. And you can kind of see the staircase emerging. And you can imagine that as I take n to infinity, I'm going to get something that basically looks like a straight line until it hits 1. And the nice thing about this is the CDF makes sense as n goes to infinity, whereas the PMF makes no sense because it just went down to 0 and there's nothing to really reason about from there. Whereas the CDF actually just became this straight line. And okay, I have a little bump in the line that I drew there, but you should just imagine that to be straight. Okay, so this is the thing I want you to take away. So the PMF values, as n increases, they go down to 0, but the CDF is very well behaved. Okay, and specifically as n goes to infinity, it was reasonable for us to take the model that f of y is equal to 0 before y equals 0. It's y between 0 and 1, and it's 1 afterwards. Okay, so drawing that, it's just slope 1 between 0 and 1, and then it's flat. Okay, that's very nice. And this is great. So I actually have something that's going to work for me for these random variables that fall on, intervals of the real line. But it would be really nice if I instead also had a way of representing the fact that all the positions between 0 and 1 are equally likely. And the idea that we have for that is just to take the derivative. Okay, if I take the derivative, I'm going to recover something that gives me that idea. So let's take the derivative. What's going to be 0, and then 1, and then 0, right? So the derivative is only going to be 1 between 0 and 1 because that's where it's equal to y. So visually, it's just going to jump up, be flat, and then jump back down. And so the flatness here captures the fact that any point in 0, 1 is equally likely. Okay, so this is nice. So I actually got something like the PMF. It's kind of the derivative of the CDF in this case, but it actually is capturing this idea that I have equally likely. But note that the probability of landing on any particular value of y is actually 0. Okay, so the fact that this derivative is 1 does not mean that the probability is 1. That wouldn't make sense for all of the values to have probability 1. This is just a thing to help us visualize and understand that it's equally likely. Okay, so let's go back and recall the cumulative distribution function. So recall the CDF. So we're going to use this as our building block as we go ahead. We just did this in the example, but we're going to do this a bit more formally. So the CDF f of x is the probability that a random variable x is less than or equal to the value little x. So formally, it's the probability measure of the outcomes that map to x that's less than or equal to x. And the shorthand we had is this set of x less than or equal to x, or even just dropping the curly brackets and just kind of remembering that they're there in the back of our heads. Okay, so that's kind of our definition for the CDF. And we did this for discrete random variables. Here we're going to see different kinds of CDF. So here the CDF, we're going to say that it's continuous if it has no abrupt changes, meaning that if I take the limit as this epsilon goes to 0 of f of x plus epsilon, I should get f of x for all x. Okay, so what does that mean? So visually, here's what could happen. I could be going along on the CDF and then jumping up, and that's a discontinuity. So that's not continuous. Whereas if I proceed smoothly along everywhere, that's continuous. Okay, that's all that I'm saying, that I don't want to see any abrupt changes or discontinuities. And if there are no abrupt changes, I'm going to say it's continuous. Okay, so a random variable is going to be called continuous if it has a continuous CDF, like we just saw, and we need one more thing. This CDF is differentiable almost everywhere. Okay, so let me unpack that. What is almost everywhere? It means everywhere except for a countable number of values where I don't necessarily need to have a derivative. So it's okay if there's no derivative in a few spots. A few is countable, but just think, for our purposes, think of a finite number of spots where there's not necessarily a derivative. That might also seem a bit weird. We're going to see an example of exactly why we need this in a moment. But first, let's just talk about derivatives. So recall that we can say that g of x is differentiable, or it has a derivative, if the derivative g prime of x, which is the limit as epsilon goes down to 0 of this function, exists. Okay, so g of x plus epsilon minus g of x divided by epsilon. So I'm just trying to see how much change I have as epsilon goes down to 0. I want this thing to exist. It seems like it kind of always exists, but let's actually see in our little example that we just did, where I had this CDF that was flat and then going up with slope 1 and then 1. So, just to draw it, here it is. So we already saw this, okay? Here's my CDF. It goes with slope 1 and then it's flat. The derivative exists here. So here's a nice spot where I have a derivative. If I take the derivative, then I'm just going to get 1 because it's slope 1. So that's nice. But let's check that formally. But first, let me tell you that here, there's not going to be a derivative. And that seems a little bit strange because this was supposed to be our nice example where everything worked out and everything was nice. And this is kind of why I'm highlighting this to you, that it's totally fine to not have a derivative in a few spots. There's no big deal. And in fact, if I didn't point it out to you, you might not have noticed and you would have been completely fine. So let's proceed. Okay, so what is the definition we had for this derivative? It's that at half, let's say I go and I start to take the limit as epsilon goes down to 0, okay, at the point 1/2. So let's look at this red spot that I'm highlighting. It's kind of going down. I'm trying to understand the function from there. So this is the limit as epsilon goes down to 0. And looking at it, it should be a half plus epsilon minus half divided by epsilon, and that's 1, right? Because I plugged into the CDF at a half plus epsilon, and if epsilon is tiny, then I'll be between 0 and 1. So I just get the value. So that's a half plus epsilon minus a half is 1, right? So the whole thing is just going to work out. Okay, what about the limit from the left? I can also approach from the left. I'm going to get the same thing, right? And that makes sense. So the limit from the right and from the left are equal, and therefore we say the derivative exists. When does it not exist is at this red point. So if I go down at this red point and I start from the right, I'm coming from slope 1. So I'm going to plug in these numbers, but the point is I'm going to get slope 1. But if I come from the left, okay, so if I send epsilon up, then I get slope 0, right? And I can plug in and see that that's true. Okay, I get slope 0. So in this case, the limit from the right and the left do not agree. So we have to say that their derivative does not exist at x equals 0. Okay, so I kind of sped through this a little bit, right? And in fact, that actually jumped. Okay, so I kind of sped through this a little bit, but the point is that it's okay if I don't have a derivative in a couple of spots, right? It's okay to have these sudden changes in slope as long as there aren't too many of them. And we're not going to really run into any examples where that would be a problem. Okay, so with that in mind, so basically just saying don't worry about that. With that in mind, let's go ahead and define the probability density function. Okay, so the probability density function, which we're going to denote with this little f of x. So this is something that's associated with a continuous random variable, and it's just the derivative of its CDF, f of x. Okay, so big F is for CDF, little f is for probability density function, or PDF. Right, let's write that down. So it's just a derivative where the derivative exists. Okay, so if there's actually a derivative, it's the derivative, and otherwise I don't really care what it is. It's fine. I can just say it doesn't matter. I'll just put in any value. Okay, so, and that's kind of what we were seeing before. So let's look at an example. It'll be more clear. So back to our usual example, I'm 0, then slope 1, and then flat again. Here's my CDF. So the derivative of this is just a box, and it's a box between 0 and 1 in the case that we saw, right? And the point is, I can really put at these transitions where I'm jumping up from 0 to 1 and then back down from 1 to 0, it's okay that there's no derivative that's formally defined. I can set those to be any values that I want. And in this case, it would be the most convenient to set them to be either 0 or 1. Okay, that's what we would do. And we probably would have done that without thinking about it, right? And that's kind of what I want you to be able to do. Just don't worry about it. It's fine if there's no derivative there. Here's a case where it's kind of smooth. Here's a continuous CDF with a derivative everywhere. And so I take the derivative, I get some bump that looks like this. And here's the thing I want you to keep in mind. Look at this PDF. It exceeds 1, and that is okay. It is okay for the PDF to exceed 1 because the PDF is not the probability of a value, okay? Specifically, the PDF is not telling us the probability that x is equal to little x, okay? This is always going to be 0 for a continuous random variable, okay? And the way to kind of remember this as like a shorthand is, let's say I play this kind of strange Wheel of Fortune game that we had in the beginning, where you have to pick a number down to the infinite decimal place and bet on it. And then I'm going to spin the wheel and measure the position of the wheel down to the infinite decimal place. And you win if you get all of the decimal positions correct. Now, it makes sense that you're never going to win, right? So like that's just too unlikely that you would guess all of these infinite digits correctly and have it show up. Okay, so the probability is just going to be 0. Okay, so instead, how should I think of the PDF? I should think of the PDF as the density of probability around x, not the actual probability of x. Okay, so here's a plot, here's a PDF. Let's say what I want to know is the probability that x lands in this interval a up to a plus delta. I can approximate this, okay, by the area of this box. Okay, so here's a box, and I've drawn a box of height f of x at a, and I've drawn the width of the box to just be delta, which is the length between a and a plus delta. Okay, so I can approximate this probability with delta times f of x, which is the area of this box. Okay, and this approximation quality is going to get better and better as delta gets smaller and smaller. And if this sounds like integration to you, you're exactly right. This is integration. Okay, so this is a good approximation of the probability of landing in that interval. So let's actually work out the probability. So it turns out the probability is just area under the curve, like that. Okay, so if I want to know the probability of falling into an interval, so in this case, I want to know the probability of falling in between a and a plus delta, then it's just going to be the integral from a to a plus delta of f of x dx. And this is how we're going to use the PDF. The PDF is going to play the role of the PMF, but we're going to replace sums with integrals. Okay, that's it. So we just have to remember that there's no interesting information in evaluating the probability of a point. That's always 0 for a continuous random variable, but the probability of an interval we can get from an integral. Great. So what are the properties of the PDF and the CDF in this case? Okay, I'm going to make a table for you. So here's the PDF side, here's the property name, and here's the CDF side. So the first one I'm going to deal with is non-negativity. For the PDF, it's going to mean that it can't be negative. For the CDF, it means it's non-decreasing. Next is normalization. For the PDF, it integrates to 1, and for the CDF, it means that if I look all the way to infinity, it's going to be 1. And also, we kind of remember that at negative infinity, it's 0. And remember, back when we defined the CDF, we said that plugging in plus and minus infinity really mean taking the limit as x goes to plus infinity or minus infinity. But let's not worry about that for now. And what if I want to know the CDF, but I have the PDF, or vice versa? Well, the way to get the PDF is to take the derivative of the CDF when the derivative exists, and otherwise I can put whatever value I want. And to get the CDF, then I go backwards, I take the integral. So I take the integral of the PDF, I get the CDF, and here I'm just using this integration variable u, so I don't get confused by the fact that x is both in the limit and in the thing that I'm integrating. I shouldn't conflate those two things. So I'm just using an integration variable that's going to get washed out. All right. Finally, I can calculate the probability of an interval. So the probability of an interval is just going to be an integral on the PDF side, so from a to b, and it's going to be a difference on the CDF side, f of xb minus f of xa. Okay, and the nice thing for continuous random variables, it's really convenient, is that since the probability of any value is 0, the probabilities of open intervals and half open intervals and closed intervals are always the same. So this is a nuance that we were paying quite a bit of attention to when we were doing calculations for discrete random variables, whether something was less than or strictly less than some value. And for continuous random variables, it doesn't matter because these are all the same. A single point always has probability 0, so I just don't worry about it. Let's do an example. Let's say that I have a random variable x that's equally likely to take any value between half and 3/4. Okay? And that's all the information I'm given. So this is kind of my problem, and I'm asked to determine the PDF. Okay? So it's easier in this kind of setting. So this is a really simple setting. It's easier to start with a plot, okay, and just to visualize what's going on. So let's do that. It's equally likely, so we know the PDF will be flat. Okay? So here I'm going to draw the points 1/4, 1/2, 3/4, and 1. And I know that it's going to be active between 1/2 and 3/4. So I'm just going to draw a box that goes up between those values. And then the only thing left for me to do is determine its height. Okay, so how high should it be? Well, remember the thing that I need from the PDF is that it normalizes to 1 when I integrate. So in this case, I need to set the height so the area is 1. meaning the integral is going to be 1. Right? Well, the area is just going to be the height times the width. So it's going to be 4, in this case, times 3/4 minus a half is equal to 1. So the reason I picked 4 here is so that this width of a fourth multiplied by 4 is 1. So now I can just write down my PDF. It's going to be 0, except between a half and 3/4, where it's going to be 4, right? So it's going to be flat between half and 3/4, and it's going to go back down to 0 after I get past. Okay, and let's work out the CDF, just so we have a nice complete picture. So let's say I want to just guess the integral from the plot. Okay, so that's one option. I can just guess the integral by staring at the plot. Totally fine. Okay, so I'm going to do that. Here's the CDF in purple. So I'm looking at the plot. The slope is 0, then it's going to be 4, and then it's going to be 0 again. It's going to be flat. Okay, so between half and 3/4, the slope is going to be 4 because the PDF is actually my derivative. Okay, I'm done. I could have also computed it directly, and in some problems I won't be able to guess from the plot, so it's good to see this kind of calculation a couple of times. So let's go ahead. I'm going to just write this out very carefully and try to show you every step. Okay, so here's the Cdf formula. To get it from the PDF, I just integrate from minus infinity up to x, because I'm looking for the probability that x is less than or equal to the value little x. Okay, and now I have to be careful because when I do this integral, there are going to be multiple cases. So the first case is when this value x falls, falls before 1/2. In that case, the PDF is just 0. So I'm just integrating 0. So if I'm looking for the CDF before x is 1/2, I'm just integrating 0 all the way, and it's going to be 0. After I've crossed 1/2, I've now broken up the integral so that it goes up to 1/2 where it's 0, right? So I'm integrating all the way up to 1/2, I get 0. And then after 1/2, I get this other piece of the integral. So I go from 1/2 up to x, and I get 4 du. And that's when x falls between 1/2 and 3/4. So this is where my integral ends in the interesting part of the PDF, where it's gone up to height 4. And now after I've crossed through the interesting part of the PDF, I'm going to get the integral up to 1/2 for 0, the integral from 1/2 to 3/4 of 4, and then I'm back down to 0, and I integrate from 3/4 up to whatever value of x I have. Okay, that's after x is larger than 3/4. Okay, so what we're going to see is that this top part is obviously going to be 0, right? And that's when x is less than 1/2. This next part, the integral is pretty simple. I can just write it down directly, right? So the integral is just going to work out to be 4u, and then I can plug in x and 1/2. So I get 4x minus 2, right? And so that's going to be between 1/2 and 3/4 for x. And this last part is just going to be 1. And I could work out the integral for that, but I don't need to, right? So you can check that when I plug in 3/4 into this integral, I'm going to get 1. But the point is, once you've integrated out the whole PDF, you must be left with probability 1. Okay, so you can just use that fact to skip any calculations that you see here. Let's stick with this example and do some probability calculations. So here's the example. I'm going to try to determine the probability I fall in the interval, let's say between 1/2 and 7/12. Okay, so I can do this in two ways. I'm going to do it with the PDF and the CDF. Let's do the PDF first. So for the PDF, the probability is the area between 1/2 and 7/12. So I'm just going to trace that out and fill it in. And this is the area. And okay, in this case, I could just guess the area by staring at it, but we're going to do the integral so we see exactly what's going on. So the integral is just going to be from 1/2 to 7/12 of the PDF. I plug in the value of the PDF there, it's 4, right? Integrating from the same limits. And so I have the integral 4x from 1/2 to 7/12. And so that's going to be 4 times 7/12 minus 1/2. And so that's just going to be the difference. So it's going to be 4 times 1/12, which is 1/3. And looking at that plot, it makes sense that I've got 1/3 of the area. Okay, great. So now I'm going to pass on to do the same calculation again from the CDF. I'm going to see how does the same kind of calculation work out if I use the CDF. In the CDF, I don't take integrals. I've already taken the integral. It is the integral of the PDF. So all I do is I take the difference, right? So the formula I had is to take the difference in heights of the CDF for the values I care about. Here's 7/12 and a half, right? So the probability is the difference in heights on this plot, all right? So I can see it's going to be a third, which is great. It matches what I had before, but let's do it formally. So I'm going to plug into the CDF at 7/12 and a half and take the difference. So I get 4 times 7/12 minus 2 minus 4 times a half minus 2, and that works out to be 7/3 minus 2, which is again a third. So great, it makes sense. I got the same answer both ways. Let's do one more calculation before we wrap up. Okay, I am going to redo this kind of interval calculation, but now I'm going to be interested in the probability of falling between 5/8 and 1. Okay, let's do the PDF calculation. And I'm kind of used to this now, so I'm going to try to speed through it. So I'm just going to write down the integral from 5/8 to 1 of the PDF. And I'm going to plug in the value of the PDF. It's going to be 4. So here it is, 4 dx. And I'm going to get, this integral is 4 times 1 minus 5/8. And I'm going to get 12/8, which is terrible. Okay, this is greater than 1, which is really, really bad. Probability cannot be greater than 1. If you ever get probability greater than 1 in anything like a homework or an exam, then you need to back up and try to figure out where you went wrong. And in this case, where did I go wrong? Well, it turns out that this integral is wrong. Okay? We're going to see why. The integral before it is fine. This one, where I plugged in the value of the PDF, is wrong. And if I look at my plot, I'm going to see why. But first, I'm going to write out the correct integral. So what I should have written out is this two-part integral, where I was at 4 up to 3/4, and then back down to 0 after 3/4. And I've correctly split this into two cases, right? And if I work this out, it's 4 times 3/4 minus 5/8. Okay, and that's going to be a half. So what happened here is I was not careful, and I didn't notice that my PDF actually heads back down to 0 after 3/4. So when I'm calculating the area, I should only have height of 4 between 5/8 and 3/4. So this is one thing, one pitfall, that when you're using the PDF to calculate probabilities, you do really have to pay attention case by case. Let's see how it works in the CDF. Okay, so the probability is the area in the PDF. Let's see how it works in the CDF. So the nice thing about the CDF is that we just won't run into these problems. So let's just see why. So I'm going to take the difference in heights. So I'm going to plug in 1 and 5/8. And so I'm going to have 1 minus 4 times 5/8 minus 2, right? So that's going to work out to be 1 minus 5/2 plus 2. And that's going to be a half, which is the same, which is great. Okay, and so visually what was going on is I went to 5/8, I found that the height there was a half, and I took the difference in heights. Okay, and the difference in heights was just a half because I was going from 1 down to a half. Okay, and the great thing here is that since we've already worked out the integral in a way to get the CDF, I don't need to be as careful. So in the CDF calculation, I've taken advantage of the fact that I was already very careful in setting up all the different cases when I, supposedly integrated the PDF to get to the CDF. I was already being very careful case by case. Okay, so hopefully I've already got it right, and then I don't need to worry when I'm taking the difference. The pitfall can be that I miscalculate the CDF case by case, but then that's just an error that I've already made that's propagating to this step. Okay, and that is it for continuous random variables.